So in my previous classes, I've already told you about the classification of engineering materials and also the applications of all these engineering materials in different fields. Now, today I shall talk about the relation between structure and property. Structure and property. The relation between structure and property. So, for this, let us take one example. Let's say we have taken two similar steel pipe, one is normal one without any annealing process and another is annealed steel pipe. One is annealed, another is without any annealing process, which is normal one. So whenever we will put some pressure on the both bar, the deformation for the both bar will differ. So now I will show the how the deformation will done and how it will be seen found in after the deformation. Here you can see, so after deformation this type of structure you can find. This is ring after ring, ring after ring, this type of symmetrical structure, symmetrical rings you can find for the normal steel. Normal steel without annealing, and this one is annealed one. So here you can see some diamond shape are there, some diamond shape are approaching in this case, but in this case which is normal one without annealing process, you can see a fine structure in this case. So if we draw the stress strain curve for these two, for these two, the stress strain curve will differ. This side strain and here in this side stress. Now we will draw the stress strain curve for these two structures. One is normal steel, another is annealed steel. So first of all, I will draw the stress strain curve for the normal one. So this is for the normal one, and for the annealed steel, it will first of all this will come like this, then this. This is normal steel, and this is annealed steel. This point is called yield point. This point is called yield point. And from this point to this point, this is strain hardening. Strain hardening. So what is basically yield? Yield one is deform a lot before it fails. Deformation of the material in a huge range before it fails as per the internal structure as per the internal structure of that material has been changed a lot before deformation. So now I will show you the internal structure for the both cases, for the normal steel without annealing and the annealed steel. So this is the internal structure for the annealed steel. So this one is normal one. So here you all can see that the difference between the microstructure of all these two cases. The grain structure of the normal steel is very fine, and grain structure of the annealed one is of course grain size. So I have already discussed about fine grain and coarse grain and the effect of all these fine grain and coarse grain in the properties of material. So these are coarse grain and these are fine grain. So for annealed one you will get coarse grain. Due to this the deformation was like that, and for the fine grain for the normal steel, here it is fine grain, that's why the deformation was like that. So in both cases deformation has been changed. So this is the relation between structure and property. So if the structure has been changed, you can say the grain structure. There are two types of grain structure, fine grain and coarse grain. If the structure has been changed, properties of material also has been changed. Here in this stress strain curve also you can see here, in this case this one is the normal for the normal steel, and the properties you can see uh, the deformation for this case and deformation for this case, both are totally different. So all these depends upon the structure, depends upon the structure of the material. Here also you can see the deformation in these two cases are totally different. So with these structures, grain structures, all the properties has been changed. Now our next topic is equilibrium. So here we have done with that relation between structure and property and now we shall talk about that equilibrium. So here you can see three similar blocks, three similar blocks are there. One, two, and three. So for all these three cases, different amount of that energy, potential energy is there. Number one and number three, these two are stable position. These two are in equilibrium as the potential energy is minimum in these two cases. But here, this is the center of gravity line. This is the center of gravity. So the number two is having maximum potential energy, due to which it always wish to come in a equilibrium position, either in this side or in this side. If we give a little amount of push over there, it will go in a equilibrium state. But here in these two cases, we have to give more amount of force to change their positions. Here, to change its position, we have to give a very little amount of force in this block. But in these two cases, we have to give a lot of force to change their positions. Number three is more stable, as the block is lying in its larger area. That's why it requires more maximum force to change its position than this position. Now I am drawing a graph of the graph between potential energy and configuration. Potential energy and configuration. You can see in this place. So this is one here in this side configuration, and in this side potential energy. So this is number one position. This is number two, and this is the most stable position, which is number three. So here in this case, minimum minimum potential energy. Minimum potential energy. In this case, maximum potential energy. So this is the graph for all these three configurations. Here you can see this is the configuration versus that potential energy, and you can see for the number two positioning, the amount of potential energy is maximum. So one is local local minimum, one is local minimum, and three is three is also minimum, but 3 is more stable as it lies in its larger side. So this is global minimum. One is local minimum, and this 3 is global minimum as it has minimum amount of potential energy. So what is equilibrium? Now what is equilibrium? If an an infinitesimally small perturbation does not change the energy or state of a rectangular block then we will call, or we will say, it is in equilibrium. If an infinitesimally small, what is infinitesimally small? Infinitesimally small means limit del x tends to 0. Limit del x tends to 0. So if an infinitesimally small perturbation does not change the energy or the state of a rectangular block, then we will call it as it is in equilibrium. So now stable or stability. What is stability or stable position? If the equilibrium is stable, the equilibrium is stable if a small perturbation does not change the state or energy of a configuration. Equilibrium is stable if a small perturbation does not change the state or the energy of that configuration. Now different types of equilibrium are also there. First is stable equilibrium. Stable equilibrium. Stable equilibrium means minimum energy. It will have the minimum energy. Then unstable equilibrium. Maximum energy. Maximum energy. Unstable equilibrium. Maximum energy. Then we will come to metastable. Metastable. Metastable means local minimum. I've already discussed about that local minimum and global minimum. So metastable means local minimum. Metastable means local minimum. Then, sorry, most stable. Now it will come most stable. Most stable. Most stable is global minimum. So here, this is the global minimum. This one is the global minimum. This one, number 3 position. And this is local minimum, number 1 position. Local minimum and global minimum. So global minimum is most stable and local minimum is metastable. So these are like the examples are pure metal like Fe, iron, then aluminium, gold, iron, aluminium, Ag, Au, all these metals means pure form. But these are stable, but these are metastable. Metastable. We will not get all these as pure form or very little amount of pure form. But most stable, which are the most stable? Fe2O3, Al2O3, CuSO4. These are most stable. These are most stable. In this case, it is global minimum and energy is minimum in this case. Energy is minimum in this case. That's why it is most stable and it is global minimum. So with this, our today's class is over. Thank you.